Hello, this is Dr. Gardner. We're going to be talking about concentrations of solutes in solutions. As you recall, when a solute, a compound that's usually present in a smaller quantity than the solvent, which is usually present in a larger quantity, is dissolved, well, the solvent is dissolving the solute by separating the individual particles. Now, these could be molecules of the solute or ions of the solute potentially, or in some cases for atomic species, it could be atoms of the solute. When those species are being dissolved into our solvent, they form a solution, which is a homogeneous, uniform mixture down to the very small levels. Now, when we consider concentrations of solutions, we might want to consider just how soluble a solute is. Now, earlier in the course, we learned how to predict solubility based on a series of solubility rules. So you should make sure you review those solubility rules and you still recall how to predict if ionic compounds are soluble or not. You also want to be familiar with how polar solvents tend to dissolve polar solutes, and nonpolar solvents tend to dissolve nonpolar solutes. So those are some important things to remember, but what we're going to focus on today is different aspects of calculating how soluble a solute is, as well as calculating various forms of concentration that we can report quantitatively. So first of all, let's consider if we look up the solubility of sodium chloride, a very common ionic compound that you probably know better as table salt. It has a solubility of about 38 grams of the solute, which is the sodium chloride, for every 100 grams of the solvent, which is the water. Now you'll notice that solubility tends to change with temperature. Most ionic compounds become more soluble as temperature increases. This is actually very different than gases. Molecular gases will tend to be less soluble as temperature increases, but ionic compounds, the solubility is usually increasing. So if we measure the solubility of sodium chloride at close to room temperature, about 25 degrees Celsius, you can dissolve about 38 grams of sodium chloride in 100 grams of water once you reach the saturation point of the water. If we go ahead and consider then the following scenario, let's say that we try to dissolve 45 grams of sodium chloride in 150 grams of water. Would we be able to dissolve that much sodium chloride? Okay, so if we recall, in this case, that we have 45 grams of sodium chloride for every 150 grams of H2O, this would be the same ratio as 30 grams for every 100 grams of water, right? There's 15 grams for every 50 grams of water, so we have 30 grams for every 100 grams of water. And if we look back at what our solubility was that we looked up, then we know 30 grams of sodium chloride is less than the 38 if we're at 25 degrees Celsius, so we haven't reached the saturation point. So I would predict that all 30 grams of the sodium chloride should dissolve. So this solution is unsaturated. It contains less sodium chloride than would be soluble in 100 grams of water. Now there's a few different ways we could determine units for concentrations of solutes in water or other solvent systems. We could perform the following types of calculations, which you should practice in this chapter. You can calculate the percent by mass, the percent by volume, a mass to volume percent. You can calculate what's called ppm, parts per million, or ppb, parts per billion. You can also calculate molarity, which we've seen earlier in the course. We use the capital M for molarity. Remember, that's your moles of solute per liter of the solution mixture. We're also going to be talking about molality today, which is a lowercase m. So whether you use capitalization or lowercase scenarios with the M is very important, signifying different concentration units. So let's define all of these different types of calculations and then practice a few of them. So first of all, if I calculate my percent by mass is going to be the grams of the solute divided by the grams of the solution mixture. Now notice this is the solution, so it is everything present in the mixture. Then you multiply by 100 to get your mass percent. Now, if you want to calculate your percent by volume, you can take the volume of the solute divided by the volume of the solution times 100%. Now, a lot of times what you'll want to do to really indicate what you have here, after you have your percent, it's nice to put an M over M to indicate that you're dealing with a mass percent and mass of solute over mass of solution. Or if you're doing with percent by volume, after your percent for your final units, sometimes it's good to have a V over V to indicate that you're looking at a volume ratio. Now if I calculate the mass per volume percent, this would be the grams of solute per volume of the solution mixture. In that case, I want to have an m over v after the percent to really indicate which of these three different similar types of calculations you may have performed, because each one of them could be reported in a certain percent value. If you don't put the m over m for mass percent, or v over v for volume percent, or m over v for a mass to volume percent, it would be very difficult to know which one of these that you were looking at unless you knew how it had been prepared. Now if I want to look at ppm, ppm is parts per million, and what you do here is usually this is used when we have very low concentrations. It's often used when we're dealing with pollutants in the environment, in water systems or the air. We can take the grams of the solute divided by the grams of the solution, but you're going to multiply by 1,000,000, 10 to the 6th. That will give you a value in parts per million. Now if we want to look at parts per billion, well again we just take the grams of the solute divided by the grams of the solution mixture times 1,000,000,000, basically 10 to the 9th. Okay, so that's how we would convert to parts per million or parts per billion. And they're really only a good choice, in my opinion, for calculating your concentration units when you're dealing with very small values of your grams of solute in the solutions. Then ppm and ppb would be quite useful. Now, as we've used molarity in the past, we use a capital M for the unit value for molarity when I'm abbreviating it. Remember, that's your moles of your solute per liter of the solution mixture. Now, realize this is liters of the solution, not liters of the solvent. So it's important you know that difference when you define this concentration term. That's not to be confused with molality, which is a lowercase m, which is the moles of solute per kilograms of the solvent that you're adding. So this is something that tends to be frequently confused. Students will forget that when they're dealing with molarity, they have liters of the solution, and when they have molality, they have kilograms of the solvent, not the solution. Okay, so you need to know those differences. Make sure you memorize each of these different simple calculations for determining concentration units of a solute in a solution mixture. So let's practice calculating a few of these. Let's say that we'd like to calculate mass percent of a solute. In that case, I take the mass of the solute divided by the total mass of the solution. So that would be the mass of the solvent plus every solute present if it's a complex solution mixture, and then multiply by 100. Okay, if we want to find the mass of the solution, as I said, just add the mass of the solute, or any solutes present if there's more than one, to the mass of the solvent that you're using. So that would be easily weighed in the lab in order to find that value. So let's practice a brief calculation with this. Let's find the percent by mass concentration of acetic acid in a vinegar solution that contains 2.70 grams of acetic acid and 122.8 grams of water. Okay, so in this case, the mass of the solute would be the 2.70 grams, and the mass of the solvent would be the 122.8 grams of water. If I want the mass of the solution, I'm going to have to add 2.70 plus 122.8. Okay, so when I calculate that to get the mass of the solution, we end up taking 2.70 grams divided by the mass of all the components in the solution mixture times 100 gives us 2.15%. As I said, if we want somebody able to read this in our notebooks and remember where we're getting it from, when we're doing a mass percent, sometimes you'll see an m over m to indicate that. So you have a mass ratio when you calculated that percent. Now let's consider if we want to find, let's say, the mass percent of sodium chloride table salt in a solution that's prepared by taking 10 grams of sodium chloride to 50 grams of water. In that case, your mass of the solute, which is the sodium chloride, would be 10 grams. And then if I take the mass of the solute plus the mass of the solvent, which was the 50 grams of water, multiplied by 100, it gives me 16.7% by mass. So again, I often want to put an m over m here so I can remember this was calculated with the ratio of mass of solute versus mass of the solution mixture of solute and solvent. Okay, let's calculate percent by volume. If I'm calculating percent by volume, we're looking now at the volume of the solute that we're measuring out. And this is quite useful often with liquids that I can measure, let's say, in a graduated cylinder or in a different type of volumetric glassware where I can find a volume of the solute just as readily as, let's say, taking a mass on a scale. Then I divide that by the total volume of the solution mixture, and a lot of times this would be a total volume when you dilute a solute in a solvent to, let's say, the volume of a volumetric flask. So your volumetric flask would tell you exactly what volume the components of everything in the solution add up to. So those would be a case where this would be quite useful. So what we're going to do to determine the volume of the solution is we're going to have to measure it. Realize that the volumes are not going to be additive when I add the volumes of the solute and the solvent, because the way the particles pack together when I form the mixture may actually cause the spacing to be greater or lesser than they were apart. So the volumes can change. In some cases they could decrease from the volumes of the original components. So I can't just add them like we were with the masses. I'd actually have to measure it. Okay, so here's an example. We take 205 milliliters of ethanol. We're dissolving it in sufficient water to give a total volume of 235 milliliters of everything combined, which would be the ethanol and the water components. So let's find the percent by volume concentration of ethanol. So I'm going to take the volume of the solute. The volume of the solute here, we could define that as the ethanol. The total volume of the solution would be the ethanol and water. Okay. So if I calculate this, we can see we have 205 milliliters of ethanol divided by a mixture total measured volume of 235 milliliters multiplied by that 100 is 87.2% ethanol. I suppose you could argue that the ethanol was more of a solvent since the percentage is so high, and perhaps you could argue the water was the solute. It all depends on your viewpoint as to what's doing the dissolving and what you consider being dissolved as well. Now, since this is a volume percent, sometimes you'll see a V over a V for a volume percent in this case to make sure that we remember where we're getting that percent value from. Now, a mass per volume percent is very similar to what we've already been calculating. You can take the grams of the solute divided by the volume of the solution times 100. This is going to go ahead and give you a concentration, and if we're looking at that, that's how they might report the concentration of sodium chloride in a saline bag in medical use. So if we have 0.9% sodium chloride in a mass to volume ratio, so it would help sometimes if you're not familiar with how they prepared these, if you saw an M over V here for that relationship. So this tells us for every 100 milliliters of the solution mixture, there's about 0.9 grams of sodium chloride. That would give us, if I took the 0.9 grams of the sodium chloride divided by the volume of everything mixed together, if we had dissolved it in a volume large enough to add up to 100 milliliters and multiply by 100, we get 0.9%. Now let's just discuss how to calculate parts per million. This is the number of grams of solute for every million grams of solution. So the way we would calculate that is you just take the mass of the solute divided by the mass of the solution and multiply by 1 million times 10 to the 6th. I'm not going to go through this in any greater detail right at this second. If we calculate parts per billion, it's calculated in a very similar fashion. We're going to take the mass of the solute divided by the mass of the solution times 1 billion, and these are very useful units when we're dealing with very low concentrations, which tend to be the case when we're looking for trace contaminants in air or water, when we're maybe considering air pollution or water pollution. So you will see, for example, for water quality reports, you might see parts per million listed for contaminant levels. So that's where you're likely to run into these, and they usually abbreviate ppm for parts per million, so you see a ppm concentration. So if I see 10 ppm, there's going to be 10 particles for every million particles of the solution, or about 10 grams for every million grams of the solution mixture. And ppb is going to be the abbreviation for parts per billion that you might run into. Okay, let's review molarity for a second. Remember, in molarity we use a capital M, so we know we're not talking about molality, which could confuse us. We take the moles of whatever I'm considering my solute divided by the liters of the solution mixture. Now realize this is the mixture, so it's not just the volume of the solvent. I have to consider the volume of everything combined. Okay, so if I want to calculate molarity, let's say that we have 117 grams of potassium hydroxide. We're dissolving it in enough water that the final volume, when I dilute everything in a volumetric flask, adds up to 2 liters. So first of all, if I want to find the moles of my solute, I need the molar mass. So I calculate the molar mass of potassium hydroxide as 56.11 grams per mole. Okay, if I want to find the molarity of the solution, then what I can do is determine the number of moles of my solute. So if I had 117 grams of potassium hydroxide divided by the molar mass of potassium hydroxide of 56.11 grams per mole, we end up with knowing that we have 2.09 moles of potassium hydroxide. We're about halfway there because this is going to give us the moles of the solute for our numerator in this calculation. The denominator, which is going to be the liters of solution, it was the 2 liters in the end. So I'm taking that to put in for my liters of my solution. So I take 2.09 moles of potassium hydroxide for every 2 liters. This gives me a molarity of 1.04 molarity of potassium hydroxide for this solution. Now, you have to be careful when you're talking about molarity that you don't confuse that with a term called molality. Now, molality is quite useful when you may have different temperatures of solutions, because unfortunately if I'm measuring molarity, the volume of the solution in the denominator would vary with the temperature that we have. Whereas with molality, we're going to use moles of solute per kilograms of solvent. Since we're dealing with moles and a mass unit, we don't have to worry about these changing with temperature. So this is very useful when I want to work with solutions at a variety of temperature to report the molality, which should be constant. Okay, so my molality, as I said, does not change with temperature. We're going to just take the moles of the solute divided by the kilograms of the solvent. Now notice this is the solvent, not the solution. So it's a little different than the denominator for my molarity. Okay, so let's go ahead and calculate one of these. We're going to take a solution that contains 56.7 grams of potassium hydroxide. We're dissolving it in sufficient water to give a total mass of 245.8 grams. The molar mass of potassium hydroxide is 56.11 grams per mole. We'd like to know the molality of the solution of potassium hydroxide. So I have to realize I'm taking the moles of the solute divided by the kilograms of the solvent to calculate this. And so I need to calculate how many moles of potassium hydroxide I have. So I was told I have 56.7 grams of potassium hydroxide. The molar mass of potassium hydroxide is 56.11 grams per mole. So I have just a little bit over a mole. I have 1.01 moles of potassium hydroxide. Okay. And if I find out my amount of solvent, which I told you here was 245.8 grams, so we can convert that to kilograms. So remember, we're dividing by kilograms of solvent. So there's 1,000 grams for every 1 kilogram, so I have 0.2458 kilograms. So to calculate molality, I'm taking the moles of potassium hydroxide divided by the kilograms of the solvent, and we find that we have a molality of 4.11 molality of potassium hydroxide. I'm sure to put a lowercase m, because if I don't, I would confuse this with a different value, which would be for molarity. So make sure you know which one you're talking about and you label it clearly. Okay, so that's all the calculations we're looking at in this video. My next tutorial video will be looking at calculations involving solutions and reactions, as well as looking at titrations. Okay, thank you very much. Have a great day, everybody.